All right, today we are diving into a really fascinating paper that connects an ancient, almost mystical puzzle with some seriously futuristic technology. It's called A Quantum Search Approach to Magic Square Constraint Problems with Classical Benchmarking. And the authors are Rituparna R., Harshavardhini, and Aswani Kumar Cherukuri. So here's our game plan for breaking this down. We're going to start with the puzzle itself, what exactly we're trying to solve. Then we'll jump into the quantum solution with Grover's search. From there, we'll get into the nitty-gritty of the quantum pipeline they built, check out how it actually performed, and finally, have a real talk about the promise versus the practical reality of it all. Okay, first things first. Let's get a real grip on the problem they're tackling here, the magic square, which is actually a lot more complex than it looks. So what is a magic square? Well, it's this perfectly balanced number grid. For any size grid, let's say n by n, every single row, every column, and both of the main diagonals have to add up to the exact same number. We call that the magic constant. For the classic 3 by 3 grid, that number is always 15. This is a textbook example of what's known as a constraint satisfaction problem. Now, here's where things get, well, insane. The number of ways you can arrange the numbers in the grid grows factorially. So for a simple 3 by 3 grid, you have over 360,000 possible arrangements. But just bump that up to a 4 by 4 grid, the search space explodes to almost 21 trillion possibilities. So you can see why trying to solve this by brute force, just checking every single combination one after another, is basically a non-starter. It becomes wildly inefficient really, really fast. And this is exactly the kind of problem where you start looking for a smarter, more elegant solution. And that smarter way leads us straight into the quantum realm. So let's look at how quantum computing offers a totally new way to approach this kind of massive search problem. Enter Grover's algorithm. Now, this is one of the rock stars of quantum computing, developed way back in '96. The best way to think about it is this. Instead of looking for a needle in a haystack one straw at a time, Grover's algorithm uses quantum superposition to look at the entire haystack at once. Then it cleverly amplifies the probability of finding the needle, making it pop right out. So the key here, the absolute game changer, is something called a quadratic speedup. If you have a list of n possibilities, a classical computer might have to check every single one in the worst case. That's a complexity of O(n). But a quantum computer running Grover's needs only about the square root of n checks. That's a fundamental, massive improvement in how fast you can find an answer. Okay, so theory is one thing, but how did the researchers actually put Grover's algorithm to work on this problem? Well, they designed this really slick 5-stage quantum pipeline that acts as a blueprint. The whole process is really neat. It starts on a classical computer, just to do a bit of cleanup. Then it goes fully quantum. All possible solutions are encoded at once into a superposition, meaning the system is considering all of them simultaneously. Then a special oracle is built to find the right answer. Grover's algorithm does its amplification magic, and finally, a measurement collapses the system and hopefully reveals a valid solution. Now this oracle, this is the secret sauce. It's a custom-built quantum circuit that checks if a potential solution meets all the magic square rules. For any state that's not a valid magic square, the oracle does nothing. But for any state that is a solution, it tags it by flipping its quantum phase. This doesn't tell you the answer, but it's a special mark that the next part of the algorithm can lock onto. But, does this fancy pipeline actually work? Let's dig into the paper's simulations and see how this quantum approach really stacks up against the old-school methods. First up, we've got a straight-up showdown, the new quantum approach going head-to-head with the classic brute force search method. And the difference in complexity is just night and day. Brute force might have to check all 362,880 combinations. Grover's algorithm, in theory, only needs about 602 queries to its oracle. Now, you'll see the simulated runtime looks way faster for quantum. But, and this is a big but, we have to remember this is a classical computer pretending to be a quantum one, and that simulation adds a ton of its own overhead. This visual really brings it to life. What we're looking at is the actual simulation output comparing those runtimes. And below that, that's the 9-qubit quantum circuit they designed to do the job. Each of those horizontal lines represents a qubit, the basic building block of quantum info. And all those little boxes are the quantum gates that actually perform the operations. All right, round 2. Now for a much tougher competitor, classical backtracking. This is a smart classical algorithm. It doesn't check every dead end. It intelligently prunes bad search paths, which makes it way more efficient than plain brute force.
And this is where things get really fascinating. For the small 3 by 3 grid, look at those simulated runtimes. They are practically identical. And this is the punchline of the experiment. At this tiny scale, the massive effort it takes a regular computer to simulate a quantum computer completely hides any of the theoretical quantum speedup.
Which brings us to maybe the most important takeaway of this entire paper, the reality check. The huge gap between the incredible promise of these algorithms and the practical limitations of the technology we have today. And the paper is refreshingly honest about the current hurdles. Just simulating these quantum circuits is painfully slow. You also need a whole lot of stable qubits, which are hard to come by. And even on real quantum hardware, complex circuits are super sensitive to noise and errors. The bottom line is, that amazing speedup everyone's excited about, it only really shows up on problems that are way, way bigger than a 3 by 3 grid. And this quote from the paper just nails it. The research validates the method, it proves the quantum pipeline is sound, and confirms the theoretical speedup. But to actually see that speedup in the real world requires large-scale, fault-tolerant quantum computers that, well, we just haven't built yet. So at the end of the day, solving an ancient puzzle is a fantastic proof of concept. But the real question this research leaves us with is so much bigger. Imagine taking this blueprint for turning a constraint problem into a quantum search and applying it to optimizing global shipping routes, designing new life-saving drugs, or solving fiendishly complex financial models. The magic square isn't the end goal, it's just the beginning.